Hi, everyone. Let's talk about one of my favorite labs of the year, the molar volume of a gas lab. I love this lab because it's a real culminating lab that really brings together so much of what we talked about throughout the year. And as I go through this video, you're going to see all the different concepts come into play. It's a great lab to run near the end of the year, brings together a lot of information. Let's start going through it. So the purpose of this lab is to calculate the volume that 1 mole of gas would occupy at STP. If you had 1 mole of gas, now which gas? Actually, it could be any gas, because by Avogadro's law, any gas, regardless of its identity, will occupy the same volume per mole. It doesn't matter the size of the gas particles themselves. It's all the same molar volume. We're going to see if you had 1 mole of any gas, what volume would that occupy? Now, you might already know the answer right now. Does the number 22.4 ring a bell? That's the answer. Right there, just gave it away. 22.4 liters. That is the volume that 1 mole of any gas should occupy. So really, this kind of becomes a competition to see who can get closest to that. And what I love about this is, through a very simple experiment, I'll bet everyone can get within 5% of that. We tend to get excellent results with this lab. So what does this look like? How are we going to do this? Well, we're going to generate a gas, and the gas we're going to generate is hydrogen. We're going to trap a small amount of hydrogen and see what its volume is. But here's the thing. You might think, all right, let's just generate a mole of hydrogen at STP and measure its volume. Easy, right? Well, the problem with that is twofold. First of all, getting the room to STP is not going to work. First of all, changing the pressure of a room is just almost impossible. You have to mess with the HVAC system to get it to exact pressure. And the bigger problem is getting it to standard temperature. What's standard temperature? 0 degrees Celsius. Great, so we're not going to freeze all the water in the pipes. So we're not going to make the room STP. The other problem is 1 mole of gas. 22.4 liters is huge. I don't have any glassware that can trap 22.4 liters of gas. We're going to have to scale this down and scale the conditions. So really what we're going to be doing in lab is generating a fraction of a mole of hydrogen gas at a certain set of conditions, at room temperature, at room pressure, and we're going to measure that small volume that it's going to occupy. We're then going to say, what if we took that small number of moles and scaled it up to 1 mole? And what if we took the room temperature and scaled it down to standard temperature? And what if we took the room pressure and scaled it either up or down to standard pressure? What would the new volume be? What gas law does this sound like? The one where we're tweaking things and seeing what the new something would be. Well, this is going to be the combined gas law. You may not have expected me to say that because we're so used to dealing with PIVNERT at this part of the year. But we're going to be using the combined gas law. P1V1 T2N2 equals P2V2 T1N1. Now you might be saying, wait a minute, that's not the combined gas law. It's P1V1 over T1N1 equals P2V2 over T2N2. Well, that's just the alternate way of writing it. I like writing it this way without the denominators. Now, again, what are we doing here? We're solving for what the new volume would be. This one, we're solving for V2. So what are these 1s and 2s? Well, the 1s are the conditions at which we measure our data. So it's the pressure of the gas we collect, the temperature of the gas we collect, the number of moles of the gas we collect, and the volume of the gas we collect. What are the 2s? 1 mole, standard temperature, standard pressure. Now notice nothing is constant, so we're actually not going to be able to cancel anything out. We're going to be plugging in 7 numbers and solving for the 8th one. Very comprehensive lab. So let's talk about the equipment and the logistics before we start diving into the numbers. This is what the basic setup's going to look like. This piece of glassware is called a eudiometer. Sometimes I call it by its nickname, the gas collection tube, or GCT. GCT, gas collection tube. It's really just a big test tube that has lines marking volumes. It's closed on one end, open on the other end. What you do is you fill it with a liquid, the gas generates and flows to the top, and you measure its volume as it goes down. So again, this is going to start full of liquid, and I'll explain what the liquid's going to be. And as the gas generates, it goes up the eudiometer, gets trapped at the top, and starts filling it from the top down. So here's 1 minute into the lab, 2 minutes into the lab, 3 minutes in the lab, and let's say the reaction stops right here. You got yourself about 30 milliliters worth of gas. So that's how a eudiometer works. Now let's talk about what gas we're going to generate and how. Let me actually jump ahead a slide here. We're going to be generating hydrogen gas, and that's what we're going to collect. Now, we've actually collected hydrogen gas. Well, I should say we've generated hydrogen gas on multiple occasions and actually trapped it once. Think back to what labs we did. We trapped hydrogen gas in one of the tubes in the electrolysis lab. That's when we split water. We also generated hydrogen gas when we added various metals to hydrochloric acid in the types of reactions lab. So this is nothing new to us, generating hydrogen gas. What we're going to be doing in this lab is taking magnesium, adding it to hydrochloric acid, generating MgCl aqueous, or forming it, although I say that kind of in quotes here because we're not actually forming it because it's aqueous, plus, of course, H2 gas, and that's what we're looking for. 1, 2, 1, 1. So that's the reaction we're going to be performing. We're going to be taking metal, adding it to hydrochloric acid, like new acid generates. With that said, let's look a little more detail at the logistics of the actual apparatus here. So I'm zoomed in now right about here, right where the eudiometer sits in the bottom of the beaker. Now we're going to fill this with HCl, hydrochloric acid. The HCl is going to be in the tube, in the eudiometer. It's going to be in the beaker. Basically, we need a lot of HCl to be down here. Now, inside this tube is, let me phrase it this way. Where do we need the magnesium to be? It has to be right here, right in the middle, Mg. Why does it have to be there? Well, it can't be off to the side, down here or down here, obviously, because if it's sitting there, the gas is going to go up and out the beaker. It also can't be down here because it's going to, some of the gas would leak out, right? Even though most of it would go up, some of it would leak out. And you can't just put it down here and then like shove the eudiometer down, because the water, or HCl inside the eudiometer, needs to be able to flow out the bottom as the gas generates at the top. So we need this to be suspended and the magnesium to stay right here. Now, how is it going to stay there? If I just stick it there, it's not going to stay. You're probably thinking, well, it's dense, it's a metal, so it's denser than water, so it's going to sink down. It's actually not true. Magnesium should sink in HCl, which is essentially the same density as water, but it would actually float because little H2 gas bubbles are going to appear on all the surfaces and kind of lift it up like a life raft. So we need to hold it in place, not to prevent it from sinking, but actually to prevent it from rising. Now, how are we going to do that? Well, we're actually going to trap it in a cage. Yes, we're going to literally trap it in a metal cage down here so it stays. Now, you might think, isn't there a problem with this? What if we put a metal cage around the magnesium? Isn't the metal cage going to react to the acid just like the magnesium would? Depends on the metal we use. I actually should have clarified this before. In order for this to work, magnesium needs to be above hydrogen on the activity series. Is it? Yes, it is. You can check for yourself. Here's magnesium, here's hydrogen. So this reaction will occur. Well, what metals can I use that wouldn't react with the acid? Any metals below hydrogen. What are they? Copper, mercury, silver, platinum, gold. Now, I love mercury, but we can't work with it. First of all, it's a liquid. Second, it would cause severe brain damage long term. That's out. I would love to be able to use gold, silver, or platinum, but we don't have an infinite budget. So what's the best choice? Copper. By taking advantage of the activity series, we're going to wrap our magnesium in copper wire so the copper doesn't react, but the magnesium does. Another great little touch on this lab that just brings a lot of it here together. So again, logistically, your magnesium is going to sit in the cage. It's going to react in the acid. The hydrogen gas is going to go up. It's going to get trapped in the eudiometer, and the volume will fill in the eudiometer from the top down, and you'll be able to measure how much gas is produced. Let's now talk about the calculations. How are we going to actually figure this out? What numbers are we going to use? Well, this lab is all about the ones and twos, right? P1, V1, T2, N2 equals P2, V2, T1, N1. Now we're solving for V2. That's our magic goal. So we need to talk about all the rest of these. Let's start with the twos, because those are kind of the easy ones. T2 and P2. Remember, the twos are the STP conditions that we're theoretically assuming. We're going to be collecting our gas at the ones: temperature of the gas, volume of the gas, moles of the gas, pressure of the gas. Those are your ones. We're then saying, what would the new volume be if we adjusted the T to T2 standard temperature and the P to P2 standard pressure? So T2 and P2 are STP. 0 degrees Celsius, or of course 273 Kelvin, 273, not 237. I'll just write it as 273. You could add the 0.15 if you want. Standard pressure is going to be 1 atm, or any variety of that. N2 is going to be the number of moles we're looking for. And if I go all the way back to my purpose, you can see the answer is 1. We're saying, what would the volume of 1 mole be? 1 mole. And we're going to treat that 1 as like an infinite 1. If you want, you can say 1.000. Let's now talk about the ones. The ones are the actual lab data that you're going to be measuring or collecting and plugging in. Well, the easiest one is probably V1. V1 is simply the volume of gas that you collect. V1 equals the volume of gas that you collect. How do we get this? You do the lab, you read the volume that's there. Easy. Now, there is one step where we'll need to equalize the pressure. Your teacher can explain that to you later during the lab. But essentially, you're collecting gas, you read off the udiometer, boom, that's a V1. T1, that's the temperature of the gas that you collect. I'll just say the T of the gas you collect. Now, again, looking at what the setup is here, here's the gas. It's in the top of the udiometer. How are you going to measure its temperature? You're going to snake a thermometer in there? You're going to snake like one of those temperature probes? No, there's really no way to do that. We cannot measure the temperature of the gas we collect. So we're going to have to make an assumption. We're going to have to make an assumption here. Assume this equals room temperature. It's the best we can do. Assume it equals the room temperature. N1, that's the moles of the gas, and I'll clarify here, the H2 gas you collect. So we need to be able to figure out the moles of the gas that we collect. How are we going to do that? You're going to sit there and count with a microscope every mole? Obviously, that's not going to work. So we're going to use, well, why don't you think about it? Maybe you can even pause the video and think, how can we measure the moles of gas that we collect? Stoichiometry. Come on, would it be the greatest lab of the year without stoichiometry? Look back at our balanced equation here. If we're looking to figure out how much N was here, or essentially, let me put my X right there. If we're looking to figure out how many moles of hydrogen, we just need to see how much of this went in and how much of that went in. Easy. Now, we're going to be contributing a certain amount of magnesium and a certain amount of acid. We're going to have to figure out which one's the LR. And that's very important to know, of course, an important concept. So we have a choice. We can add a lot of magnesium and a little bit of acid, forcing the acid to be the LR. And then you could base it off a 2-to-1 mole ratio. Or we can do the opposite. We can add a small amount of magnesium and a lot of HCl, forcing magnesium to be the LR, and base it off of that. Theoretically, either one should work. Well, logistically, which one do I like better? I like the magnesium being the LR. I like that. Why? Well, first of all, it's easier to get the moles of magnesium. You just put it on a balance and it's done. You could find the moles of the acid, but that would require you to have the molarity of the acid, the volume of the acid. I really don't like working too much with these acids in an unnecessary capacity. Plus, I want the acid to be in excess, so it just speeds the reaction up. If we use just a little bit of acid, we'd be there all day waiting. So we're going to make the limiting reactant the magnesium, and we're going to make the excess reactant the HCl. Now, we can help that along by doing one of two things or a combination of both, either really concentrated acid or a lot of acid, or a combination of both. And we're going to sort of do more of the first one. We're going to use about 10 milliliters of 6 molar HCl. Now, you might not have a big point of reference on this because we're just starting to talk about acids, but this is really strong stuff, really concentrated. In fact, the pH of that acid would be negative. It's so concentrated. So we're going to be using about 10 milliliters of extremely concentrated acid. Depending on the size of the piece you get, you can do the numbers and actually calculate which one is the LR. I encourage you to do that. But you will find that this will be the LR by like 20-fold. We want to use an absurdly excess amount of HCl. It just speeds the reaction up. Now, how are we going to know this during the lab? It's very important that we know that the magnesium was the limiting, because if we base everything off of this, it needs to be the LR. You know, if you're mistaken, if you're actually limited by your HCl, but you base everything off the Mg, you're going to get it wrong. So think about what this would look like during the lab. Well, if the magnesium is a limiting reactant, what's the magnesium going to look like at the end of the lab? It's going to look like nothing. It's going to be fully gone. Of course, when I say gone, where's it going to end up? Well, it's going to end up as magnesium ions, which just look like regular water. So as long as the magnesium fully disappears, we will know that it is the limiting reactant, and we can base our numbers off of it. So let's go back to this slide, and let's talk about how we're going to do this. The moles of the H2 gas you collect, we are going to base this off stoichiometry from the Mg. And that leaves us with P1. P1 is the pressure of the H2 gas you collect. The pressure of the hydrogen gas you collect. Now, let's look again at what the setup is here. Your gas is going to be up here, where you see it in green. Remember I said we weren't able to really snake a thermometer in there? Do you think we're going to be able to snake a pressure sensor in there? Of course not. So we're going to have to make another assumption here. Same as above, we're going to have to assume this equals the room pressure. It's the best we can do. Well, actually, sorry, we're going to touch on this a little bit. We're going to assume the pressure in the eudiometer equals the room pressure. And you might say, why are you writing all that extra stuff there? What are you getting at? Well, let me address this first, and then I'll talk about that. Your teacher will have instructions for you on how to calculate this pressure. What I prefer to do for my classes is to look it up online from a weather website. Now, what's the alternative? Well, we do have pressure sensors in the room, but I like using the weather website, and there's a certain reason for that. When I look up the weather, I happen to Google Wilton CT weather, and look what we see. Barometer. Oh, I can't circle it here. 29.96 INHG and rising. INHG, what the heck is that? Oh, inches mercury. Interesting. Now, we're not used to dealing with inches mercury, so this gives us a great opportunity to do some unit conversions. We're bringing all the way from September back in with inches conversions. Now, what are we going to do with that? Well, you can take inches of mercury, put it into millimeters of mercury by doing inches to centimeters to millimeters. And then from mmHg, you can go to whatever pressure unit you need. So that's how we're going to find it. Your teacher might have a different source of the pressure. But what's this other thing I'm kind of getting at here? Let's look inside the eudiometer again. Where'd it go? Right here. Anytime you collect a gas by bubbling it through water, the gas is not just the thing you're collecting. Water ends up kind of getting kicked up into that gas. So the gas in the eudiometer is actually not pure H2. It's H2 and H2O. It's both of them. Now the pressure in there will be assumed equal to the room pressure. The problem is we don't need the pressure of the H2 and H2O to plug in. We need just the pressure of the H2. What law are we getting at here? Dalton's law. See how we get to use yet another gas law for this lab. Once again, the gas you collect will have water vapor in it. We sometimes refer to this as a wet gas. When you run it through liquid water, it picks up some of that water. The pressure of the water and H2 mixture is going to equal, at least by our assumption, the room pressure. But we need not the total pressure. We need just the partial pressure of the hydrogen. So how do we get that? We need to subtract out the partial pressure of water. How do we know that? We're going to use some good old-fashioned Google. All you need to do is look up the room pressure, not room temperature, the water temperature. You're going to go to a site like this, and you're going to be able to look up the vapor pressure. That's another way of saying partial pressure in this context, the partial pressure of water at various temperatures, and this is going to report it in torr. And then you just have to subtract that out of the room pressure to get just the pressure of H2. So for pressure, we could do a lot of fun gymnastics with our numbers to get the pressure. So we have all of our ones, we have our twos, you solve all 7, you plug them in, you get your answer. And you see how close you get to 22.4 liters. Let's wrap up the video with some sample calculations. Okay, so let's say you run the lab. The piece of magnesium had a mass of 0.0527 grams. I didn't even list the volume and molarity of the acid because we are going to assume that it is excess. The room temp, and by the way, we don't need to just assume. We can measure it so that it's plenty, and we can verify by the magnesium disappearing. Room temperature is 21 Celsius, water temperature 19 Celsius, room pressure from Google, 29.51 inches mercury, volume of gas collected at the end of the lab, 42 milliliters. In fact, the eudiometer is probably going to give us an extra decimal point. Let's say 0.0. All right, what are we going to do? Well, let's get our twos out of the way. That's easy. So T2 is going to be standard temperature, 273.15 Kelvin. P2 is going to be standard pressure. That's going to be 1 atm or some variety of that. N2 is going to be 1 mole. I want lots of sig figs here, so I'm just going to go infinite because, again, the 1 is like a conceptual one. And now to deal with our ones. Well, V1 is easy, right? V1 is just the volume you collected, 42.0 milliliters. Let's solve for T1. This should be an easy one. T1 is the temperature of the gas inside the eudiometer. Our assumption is that that equals the room temperature. Room temperature is 21 degrees Celsius. So this is going to be 21 plus 273, which is going to be 294 Kelvin. Let's solve for N1. N1 is the moles of gas, hydrogen gas. How do we do this? Well, we start by looking at our balanced equation, which you can see here. What's the mole ratio from magnesium to hydrogen? 1 to 1, nice and easy. So all I need to do is turn the magnesium grams into moles, apply the 1 to 1 mole ratio, and that's N1. So 0.0527 grams of Mg times 1 mole over 24.31 grams, which is going to equal 0.0527 over 24.31 is 0.00217 moles of Mg. And because of the 1 to 1 ratio, 1 to 1, This is also going to equal 0.00217 moles of H2. And finally, P1. P1 is our pressure of gas. Now, we are assuming that the pressure in the eudiometer equals room pressure, which I grabbed from Google, which is 29.51 inches mercury. But we need to subtract out the partial pressure of water at that temperature. What is that? Well, let's check our guide here, our table. So if the the water temperature is 19 degrees Celsius, let's see what we subtract out. Right there, 19 degrees Celsius, 16.5 torr. So we need to subtract out 16.5 torr. Now, can I just do 29.51 minus 16.5? Of course not, because the units don't work. So we got to do a little conversion here. Let's take our inches of mercury and turn those into torr and then subtract out the torr. All right, inches of mercury. How many centimeters are in an inch? 2.54 centimeters per inch. And yes, you can do this, linear measurements with INHG. Inches mercury, that gives us centimeters mercury, times 10 millimeters over 1 centimeter. Cancel, cancel. That will give us mmHg. And of course, times 1 torr over 1 mmHg. Now you could also do 760 over 760, they're the same thing. All right, 29.51 times 2.54 equals, times 10 equals 749.55. And I'm going to go with 4 sig figs here. The 2.54 we generally treat as infinite, and these are definitely infinite. So I'm going to go 749.6 torr. And now I can subtract out my partial pressure of water, which is 16.5 torr, which gives us our final answer, 749.6 minus 16.5, 733.1, 733.1 torr. Now you'll notice if I'm using torr here, I'm going to need to use torr there, or I could switch them both to ATM. I'm just going to turn this one into torr, nice and easy. Okay, and with that, I have all 7 values I need. T2, P2, N2, V1, T1, N1, P1. A lot of work going into these. All right, let's set it up. I'm going to have to be doing a lot of back and forth here. So P1, V1, T2, N2 equals P2, V2, T1, N1. What are we solving for? V2, the new volume. V2 is going to equal P1, V1, T2, N2 over P2, T1, N1. This is going to equal P1, 733.1 torr. It's the bottom right. Times V1, 42.0 milliliters. Times T2, 273.15 Kelvin. Times N2, 1 mole. Divided by P2, 760 torr. That's true by definition. 760, I'll just do 0.0 torr. Divided by T1, 294 Kelvin. N1, 0.00217 moles. Let's check our units. Torr cancels torr. Kelvin cancels Kelvin. Mole cancels mole. Milliliters is the only thing left. Does that make sense if we're solving for volume? Sure. Let's see what we get. 733.1 times 42 equals, times 273.15 equals, times 1 equals divided by 760 equals, divided by 294 equals, divided by 0.00217 equals. Where do I feel like I messed something up? Let me plug these numbers in again. 733.1 times 42 equals, times 273.15 equals, times 1 equals, divided by 760 equals, divided by 294 equals, there we go, divided by 0.00217 equals. Now, what did we say the answer should be? 22.4, right? So how do I end up with 17,000? Well, think of the units. It's 22.4 liters. Well, in this case, if I'm solving for ml, it really should be 22,400. I can't do my, oh, stylus just died on me. 22,400. So the answer I got was 17,300 milliliters, which is 17.3 liters. Now, I made up these numbers right at the start of this video, so that's not very good. It should be 22.4. I got 17.3. I'll bet you're going to do a lot better than that. So this lab is a lot of work. I think it's very rewarding to be able to do a simple experiment, involve all these calculations, and feel like you're in over your head, and then end up with an answer that's very, very close to 22.4. So I'm curious to see who can get closest to that. Good luck.